Okay, so hi again. So the topic of this talk is how dynamic recrystallization by subgrain rotation or continuous recrystallization operates in olivine-rich rocks. So first, why we are interested in dynamic recrystallization, and this is because all major rock-forming minerals in the Earth easily undergoes dynamic recrystallization when deformed plastically, and in fact there is no high strain rocks without dynamic recrystallization in the Earth. So for this we set a series of traction experiments, and the material we use are cylinders of 10 millimeters in diameter and 30 millimeters in length, directly coursed from natural olivine-rich rocks. The grain size is quite large, of several millimeters. And okay, the other day, Sylvie de Mouchy already explained why study olivine is very important for us, so I'm going to skip this one. Okay, these cylinders were deformed in a gas medium apparatus at 300 megapascals pressure and 1,200 Celsius degrees, which is a high temperature even for olivine. Experiment was at constant strain rate 10 to the minus 5, which is a very fast strain rate for a rock, like 8 times, between 8 and 10 times, 10 order or magnitude faster. So this requires very high megapascals, very high stresses. And finally, we quench the experiment to freeze the dynamic recrystallization microstructure. So then for every sample, we perform a very large map with a very large step size to see the whole picture, and then we locate some region of interest to study recrystallization and carry out very different high resolution maps, USD maps. Okay. So for the segmentation, we consider that a grain boundary are those interfaces that have misorientation values above 15 degrees. That is the common threshold for olivine. And then we also segmentate the dynamic recrystallized grains based on the grain orientation spreads of the grains. And the recrystallization ones are the ones that goes below 2 degrees. And then we also segmentate the candidate for parent grains, for those that are really segmented, but they are no longer the big ones. And we also segmentate the different grain boundaries just to study them separately. So finally, we also study the subgrains by assessing the contribution of the different dislocation types and systems. So I'm not going to go into much detail in the technique, but basically you have to define the dislocation type you expect to find in olivine. There are these ones, and then you can restore or partially restore the curvature tensor from the EBSD data and fit the G and D densities of the different dislocation types. So in the end, what you obtain is a plot of the densities for the different dislocation types, so you can compare and evaluate. Okay. So now we're moving into the results. So this is what a typical high resolution map look like. So the situation here, okay, extension is like this, and we have two big grains. This one, there is a grain that is in a hard position, so it's barely deformed, and this grain that is in a soft position, that is very strained. So you can see a lot of subgrains, and these are only the subgrains that have misorientations above 1.5 degrees, for the sake of clarity. And also the white stuff is another phase, so don't worry about that. We also see that they develop a lot of dynamic recrystallization grains that are mostly located in the highest strained grain, and nearby the hard grain, because it's where the stresses are located. So you can see in the subgrains that there are a lot of subgrain cells formed, and that sometimes these subgrain cells turn into real dynamic recrystallized grains, and the size of these subgrain cells are about the same of the dynamic recrystallization grains, that is like an average of 10 microns. So overall, all these factors are indicating us that the dynamic recrystallization mechanism that operates is subgrain rotation. So this is what we are going to study. And for this, we are going to answer these three questions. So our goal is to answer these three questions: is how subgrain cells form in olivine, how do they evolve to form the grains, and finally, how subgrain rotation recrystallization affect the texture. Okay. So we are now zooming into some parts of this map to look into the subgrains. First this one. So okay, we can see here a subgrain, and this is the disposition of the olivine grain. So the b-axis is perpendicular to the screen right now. So we can see that these subgrains that runs parallel to C, or perpendicular to the normal to the 100. Okay? And we can see that the dislocation type that dominates is in A is 10010. That is the easy glide system in olivine, so it's not strange. And also in the ones that are in the middle between these two, the ones that dominate is the other in A. And this kind of subgrains that runs parallel to C usually have a misorientation that locate close to C. Okay. Okay. Now we just see this kind of subgrains that runs parallel to C, but you can see that they are not the most common one. The most common ones runs like parallel to 101. They are very regular and form these subgrain cells. So we are going to focus now in these ones, and more specifically here that we can see this zigzag configuration and full loops. So first, this is the zigzag configuration. So the olivine is the same with the z-axis perpendicular to the screen, and so you can see that only two dislocation types pop up when estimating the GND densities. There is and the funny thing with these two systems is that when the high densities for this dislocation type in A coincide with the lower densities with these dislocation types in C, and vice versa. And this is easily explained because these ones are the ones that run parallel to C or perpendicular to A. So there are accumulation of dislocation of the A type, and the others that run parallel perpendicular to C are accumulation of the C type, and the ones that run oblique to both, they have about the same GND density because they are mixed with both. Another thing, another feature is that this type of subgrains always have misorientation axis around B, and this is the one that dominates in all the maps. In fact, when you measure the bulk misorientation axis, but all the subgrains, you always systematically see a maximum around B. Okay, this is exactly the same situation. This dominating these two misorientation axis also around B, but this time forming just a closed loop, and you already see the formation of these subgrain cells with these two systems. So just that. Okay, and this is another complete different sample. And this just to I'm going to focus on this one, where you can see the formation of subgrain cell and these subgrain walls here that run perpendicular normal to A, the typical that we already see with dominate A, but then to close this subgrain cell, we need another dislocation type, and in this case, this C type. That is the first time that we observed this one, and it's the less common one. Okay, but it's still there. But it is still there, and also in this case, these dislocation types are the ones that produce misorientation axis close to A. So now we are moving from subgrains to grain boundaries. Here is the misorientation axis, analysis of misorientation axis, and analysis of misorientation angles. So okay, this is the subgrains, and if I already told you, there is a maximum in B, and also a submaximum in some places, some areas in A that are related with the easy glide system. But then when you estimate the misorientation axis on the recrystallization front, okay, you still see a submaximum in B, but then there are shifts to A or to 101, so there are some kind of jumps, and this situation is even worse for the dynamic recrystallization grains, that there are several submaximas all over the area. So something is happening in here. And also when looking into the misorientation angle, one might expect that for the recrystallization front that put in contact the new grains with the parent grains, the misorientation angle should be close or not far away from the 15 misorientation angle, but you can see that the probability to find a misorientation angle of 40 is about the same to find a misorientation of 90. It is surprising. And this is just to show an example of highly misoriented grains. So the situations are three original grains and the dynamic recrystallization, and here there is an accumulation of subgrains. So this is a misorientation angle map, and the accumulation of these subgrains produce already inside the grain a misorientation that goes up to 60 degrees. But then we can see here a dynamic recrystallized grain in red. So there is a jump of 50 degrees in misorientation, and there are even more extreme cases here. These grains in orange that go from blue to orange, that is more than 80 degrees of misorientation. So maybe you can think, okay, but maybe this is not the parent grain because the reference frame is the parent grain right now. So I change the reference frame here, and misorientation with this grain, okay, decreases a lot, but then there are a lot of orange ones here, so it's getting worse. So the highly misoriented grains are still there. Finally, the texture, the final part. So okay, these are inverse pole figures. The first column are the parent grains that you have just maximas because it represents only one or two grains or two different grains. The second one is the relic grains, and the third one is the dynamic recrystallization grains. So there's I would like to highlight three features here. First is that the dynamic recrystallization diffuse the CPO, the original CPO, the original parent grains. The second is that systematically it appears a maximum around the 010 direction. Okay, in some cases this is inherited because some of the parent grains are already there, and that makes sense because this is if you plot a map with the minimum stress required for the forming an olivine grain, This is the direction that is the softest one. So these are the parent grains that are most deformed, that the ones that develop more dynamic recrystallization. But anyway, there are some examples that are not in the 101, example here, and this one disappear or shift towards the 101. So this is the axis that arrange parallel to the extension direction, preferentially. And then also we can see that there is some kind of a spread between A and C. So sometimes not the 101, sometimes more close to C, sometimes more close to close to A. So B lies perpendicular to the extension direction. And so this is more or less the situation: 101 parallel to extension, and B perpendicular, and can arrange in whatever direction within this plane. So theoretically, we will see something like this in the pole figures, with B forming a vertical girdle perpendicular to the extension direction, and A and C forming small girdles at 45 degrees to the extension direction. This is more or less what we see. This is the parent grains, and the B axis start to spread, forming this vertical girdle. During the whole evolution to the number of recrystallization grains, the strength of the fabric decreases, and the only plane that contains this A101 or C that rotate towards the extension are the 01s, the 010, that is also the one that rotates towards the extension direction. So, returning to the first question, to the question posed above, before, how subgrain threads form in olivine? Well, there are teal walls composed by all the edge dislocation types that include soft and hard slip systems. In fact, this is the most common one in A, that is soft but not the softest one. This is a very hard slip system in olivine. So these require very high stresses, and this fit with to what we observe in nature or even in experiments, because subgrain rotation usually operates at low temperatures, in our case, but also high strain rates, because it requires high stresses. So how do they evolve to form grains? Okay, there is we found a marked change in the misorientation axis from the subgrains that have a maximum in 010 to recrystallization grain boundaries that sometimes have a maximum here, but they're also in other direction. Recrystallized grains can develop high misorientation, either progressively or abruptly, and the progressive ones are easy to explain by accumulation of subgrain boundaries, subgrain walls, but we do not have a clear picture yet about how these ones produce. So, and the last question, how subgrain recrystallization affect texture? Okay, subgrain recrystallization weakens the texture, is the opposite to grain boundary migration, but at the same time there is a reorientation towards an easy glide orientation, the 101. But these mechanisms do not operate, the selection process do not operate like in GBM, because there is no selective growth. But there is a crystallographic control, and I think that these are the take-home message for today.